If textbooks say red, orange, yellow, green, blue, and violet are just different wavelengths of light, what is color actually? In the energy filament theory, color is not painted stuck onto light. It is a specific rhythm in the way the energy sea moves. From school we learned a neat story. That white light is a mix of many wavelengths and a red cloth reflects red and absorbs the rest. But that raises an awkward question. If the same white beam carries every color, why does only one shade come back to your eyes and where did all the other colors really go? In this picture the universe is not empty space with colored bullets flying around. It is a tightly stretched energy sea. And atoms and electrons are loops of that sea wound into little rings that have to stay locked in a stable pattern to exist at all. Around each loop there is a near-field texture, a tiny pattern of twists and ridges that acts like a latch. You can imagine it as a ring of teeth that grips the structure and only lets it move in certain ways without falling apart. Those latches have preferences, and their preferences are all about timing. Some patterns of tightening and release are easy for them, others feel awkward and unstable. So each type of atom likes to give away its extra energy only in a few favorite beats. Those favored beats are what we call its colors. When an electron drops from a higher energy level down to a lower one, it does not throw away its excess energy with a random shake. It chooses the beat that feels most natural to its latch pattern, the one that lets it get rid of that energy while keeping the whole loop stable. And that beat maps to one particular color of light. If the same kind of atom makes the same kind of jump again and again, it uses the same small set of beats each time. So it keeps writing the same thin fingerprints into the energy sea. In lab language those are spectral lines. But in this view they are more like notes of a musical instrument. The distinct sounds each type of matter can play on the sea. White light is just all of those beats piled together. A big messy chord with many rhythms mixed in. When that chord hits a red cloth, the loops on the surface are not neutral. Their latch patterns are especially sensitive to some slower, looser beats and much less responsive to others. When the mixed light arrives, those favored beats make the surface loops shake strongly. The loops swallow some of that motion and turn it into internal fuss, which we feel as warmth. And then they push part of it back out into the energy sea using their own comfortable timing, which happens to match what we call red. The other beats in the incoming light do not disappear for free. Some are simply eaten and turned into extra internal motion that never comes back out as light at all. And some are ray-emitted so weakly or in such scrambled directions that almost none of them end up inside the narrow cone that reaches your eyes. By the time the energy sea near your eyes finishes eating everything up, what arrives from the direction of the cloth is dominated by those red beats. So your brain quite reasonably says this surface is red. You can picture it like a room full of people clapping off beats while one group insists on clapping in a steady slow rhythm. After a few seconds the messy background fades into noise and the only clear pulse. What you can lock onto is the one rhythm that the stubborn group keeps feeding into the room. High temperature flames gave another clue. As you heat gas to extreme temperatures, you are forcing its internal loops to move faster and juggle more energy. And the only beats they can stably use to throw that excess energy back into the sea shifted toward tighter, faster patterns. So the dominant visible light slides from red and orange towards white and blue. A blue-white flame is not more pure than a red flame. It is simply broadcasting a set of more urgent beats, because its internal structures are working harder and need faster ways to dump energy while staying intact. Once you start seeing color as timing instead of painting, many familiar facts line up. Different elements have different spectral lines because their latches are carved differently. Dyes and pigments change how surfaces respond to particular beats, so they rewrite which rhythms get ray-emitted towards your eyes. Even the way colors mix begins to look like adding or canceling patterns in a shared ocean of motion. So why does light have color at all? In this picture, color is the fixed rhythm a particle uses when it returns extra energy to the energy sea. A kind of optical signature that each type of matter writes into the surrounding field whenever it breathes out. In the next episode we will ask a deeper question, not about what light sounds like, but about what it actually looks like underneath the diagrams. And we will see that its shape is neither a simple line nor a flat wave but a trapped bundle of moving textures. Tap follow, share it on New Physics, Clear Universe.